ERC20 tokens are used in practically every single DeFi protocol today. And of course, there are many intricate little edge cases or potential vulnerabilities that come along with these different types of ERC20 tokens and the different types of implementations and behaviors that you can get. And I have personally seen countless vulnerabilities and bugs and findings that stem from exactly these edge cases and weird behaviors. So of course today we're going to get to know what all of those weird behaviors, all of those edge cases are, and we're going to see exactly how those can apply and actually turn into real findings in a smart contract security review. And so there are actually 12 different edge cases, weird behaviors, or just flat out exploits that we're going to go through and we're going to cover today. But of course, before we dive into that, my name is Owen, and just about 2 years ago at this point, I founded Guardian Audits. And ever since then, our team uncovered literally over 100 different critical vulnerabilities and prevented these with security reviews that we conduct. And throughout all of those security reviews and all of those hundreds and hundreds of smart contracts that we have assessed and I've personally audited, I've of course seen a lot of things and had to personally go through and learn tons of different things about DeFi protocols, about smart contract security. And so my goal with this entire channel and everything that we put out, and especially this video, is to give all of that knowledge to you and distill it down and make it as easy to understand as possible so you can sort of fast track the learning curve that I had to go through. All right, so with that out of the way, let's dive into these 12 ERC20, or I guess just tokens in general, token integration, edge cases, weird behaviors, etc., etc. Let's dive in right now. All right, fantastic. So in just a minute, we're going to go over 12 different edge cases and weird behaviors in ERC20 tokens and just tokens in general that can often cause unexpected behaviors in protocols, or even in some cases yield actual critical vulnerabilities. Now, first of all, before we dive in, really the goal of this video is to raise the awareness of these 12 different edge cases and vulnerabilities, because that's exactly how these edge cases turn into vulnerabilities, is because people do not know about them. And so when they write a protocol, then they have some sort of bug relating to this edge case that they didn't handle. So what I want you to do is, after we're done going through these 12 different edge cases, take all the ones that you didn't previously know, write them up in a tweet, and go ahead and tweet that out, tag me in it, so we can get more eyes on these edge cases, and specifically on the ones that people do not know about, right? So take all the ones that you didn't know, put them in a tweet and share them. This will help you, first of all, remember these yourself better, because you have the tweet to reference back to. You'll remember writing the tweet, but also we're going to be sharing the knowledge of the exact stuff that we, might not be as commonly known. So make sure to keep a running list of the things that you aren't as familiar with as we get into it, and let's get started. So of course, first of all, what we have here is fee on transfer tokens, right? So you probably may have already been familiar with these, but of course we have to talk about fee on transfer, and we'll also put into this category rebase tokens, right? So what's the crux of this edge case here, right? Well, the crux of this is tokens that change balance on transfer, right? That's the real odd behavior that systems often don't handle, right? So if we're dealing with an arbitrary token, or fee on transfer and rebase tokens are specifically in scope for a protocol, then we need to worry about tokens that change balance on transfer, right? So with a rebase token, we could trigger a rebase on a transfer, and that would literally cause the tokens that you received to be the beneficiary of that rebase, and so you'd actually receive more tokens than were transferred. Or in the case of fee on transfer tokens, then of course if we're taking a fee on transfer, then I can transfer you 100 tokens, but if the fee on that is 6 tokens, you will only receive 94 tokens. And a lot of systems actually don't account for this, right? So we want to make sure that if we're ever dealing with arbitrary tokens, or we're dealing with a system that, specifically plans on supporting fee on transfer or rebase tokens, that we deal with this, right? And the way we address this is really, instead of just, transferring amount, right? As you'll usually see, like there's some variable called amount in the code. Instead of just transferring that, we want to not do that, transfer amount and assume we receive amount. This is the thing we do not want to do, right? So let's not assume that we received amount. We want to transfer amount, or whatever was specified by the user or the system or what have you, and measure the amount actually received with a balance check. So what would this look like in, basically pseudocode is, this example would look like, you got a function and we take in the amount, and then in this function, we would just say transfer from, have some token.transfer from, and this is just basically pseudocode. We'll transfer from the message.sender to this, just to make it short, to this contract, and we'll transfer the amount, right? And then we'll go on through the rest of the code and say, hey, we got amount, so let's use amount in our accounting. Do not do this. What we want to do is we have the function, we could take the same function. Instead of this, if we're going to support these tokens, what do we have to do? We've got to come in here. We have to first, let's cache, bow before could equal token dot balance of this, and we're going without semicolons here. And then we could say the actual bow received. So we're literally measuring, okay, how many tokens did we actually veritably get? That is equal to the token dot balance of this minus bow before, right? So this is literally, what is the definition of how much did we receive from doing this transfer? Now, if it is a fee on transfer token or a rebase token, this amount can possibly not be equal to the actual bow received. So hey, we got bow received, so let's use bow received in our accounting. And we'll use bow received going forward because that's the actual tokens that we actually got, right? So that is fee on transfer or rebase tokens, right? So we'll go ahead and get rid of this, put that up there. Boom. Number one, check mark. Okay. Number two, got callbacks, tokens with callbacks, or 777s, right? So this is another one that is probably pretty common. Now, we're going to go over the common ones in the beginning. We're going to get to the more esoteric and interesting things near the end, just to keep you sticking through this. But we're going through callbacks. Of course, what does this mean? This means that when we call transfer on this token, so we do token.transfer, oh, there's a reentrancy potential here, right? So the callback can call the account who is, depending on the implementation of, if it's an arbitrary token, it could call the account who is receiving or sending, and it could do so before or after the transfer is executed, right? If it's an arbitrary implementation of a token with callbacks. So we have to think about all of these situations when we're thinking about, okay, is this an arbitrary token? Could it have callbacks? Well, if it's arbitrary, it could. And then we have to think about, okay, well, is the call, the account who is receiving, is the receiver trusted? Is the sender trusted? Can they do something that could exploit the system potentially if they were able to receive execution of the transaction at this point, also before or after the actual transfer is executed, right? So before the balances of the token is updated, could we catch the system in an invalid state or something like this? And so to dive more into the reentrancy potential here and how exactly we might be able to get a reentrancy attack or reentrancy vulnerability out of this, go and watch the reentrancy guide, the complete guide to reentrancy on this channel. We'll cover every different potential type of reentrancy that could occur from this and all the risks that are associated with that. So that is all that we're going to cover for 777s. Basically to be aware that, if we're using an arbitrary token, or if 777s or just tokens with callbacks in general are planned to be supported, then what we want to do is we want to be sure there's no reentrancy potential. Boom. Okay, let's talk about now returning false versus reverting on failure, right? And this is basically the entire reason why, of course, we have safe transfer, right? So we want to standardize the tokens who are in this camp over here of they return false, or these tokens over here, which revert. These are two separate behaviors on failure of a transfer from, or an approve, or something like this. Two completely different behaviors. We want to standardize them, right? So what safe transfer does is it says, hey, you guys who return false, well, for the folks who return false, we're just going to go ahead and say, if you return false, we're going to wrap this and just have the whole thing revert as well. So we just really, what safe transfer does is it moves this circle and it makes everybody just revert. So that's how we standardize, right? But if you're not using safe transfer, well, then you had better be checking the return value to see if it's false. Even better, you should just be using safe transfer, right? So that's how we deal with this edge case of tokens that return false versus tokens that revert on failure. We use safe transfer. So let's get that out of here. And we go to that. And boom, number 3. Now we can start getting to some more interesting things. So let's talk about tokens that revert on zero address or zero amount. So some tokens may choose, especially if it's just an arbitrary implementation, if you're dealing with an arbitrary token, you have to think about tokens that will choose to not allow transferring to the zero address. So transferring to or from the zero address, that could revert in many tokens actually. Additionally, transferring zero amount to any address, that could also revert depending on the implementation of the token. So whenever you're dealing with a system, you have to think about, okay, what are the expected tokens to be used here? Do those tokens have either of these behaviors? And if they do, are those handled, or are those going to cause any sort of problem? And of course, if the system expects to work with an arbitrary token, then you've got to worry about both of these scenarios as well. And so just to see, for example, how common some of these behaviors might be. So first of all, in the actual OpenZeppelin ERC20 implementation here, we can see in the underscore transfer function that if the from address or the to address is the zero address, then it reverts, right? The transfer reverts. So we can see literally in the OpenZeppelin implementation, the transfers from or to the zero address revert. And so that's something that could potentially be used as a knob to cause a denial of service attack in a system, or maybe some sort of risk-free trade in a more complex system or something like this. So number 4 here, boom, checked off. So let's move on to number 5. And that is just no return values. So no return values. So we talked about maybe having a Boolean that returns false when you fail. What if you just have literally no return values? That is going to be an issue. First of all, let's have a look at, for example, like the ERC20 interface. And we can see that, for example, like the transfer function returns a Boolean, the approve function returns a Boolean, transfer from returns a Boolean. But if we go ahead and we have a look at the tether token here, and we scroll down to the bottom, we can see that we've got an approve function here, which has no specified return value. We've got a transfer from function that has no specified return value. We've got a transfer function that has no specified return value. So on Ethereum mainnet, USDT does not have any return values for the transfer from, and approve functions. And this can be an issue, especially when the interface that you're using expects to receive some return data back to be decoded as a Boolean. So let's have a look at Remix, we got a very simple example here where I've got an interface with an approve function that expects a Boolean to be returned here. And then we've got a function test call, which is I'm just going to basically call the token, and I'm going to attempt to return a Boolean from this function, which is something that, should be returned based on this interface. But we can see the token here that I've implemented has an approve function, but if I go ahead and remove this returns here, we can see that, okay, I'm just going to leave this function body as is. We don't actually return anything in this approve function. So let's go ahead and deploy these things. Let's deploy the test approve. Let's deploy the token. We'll go ahead and grab the token address. We come here, we pass it in, and let's see what happens. All right, so let's deploy and let's see what happens here. If I deploy test approve and then I deploy the token, and then I can go ahead and copy the token address, pass it into this function test call that, we can see that it reverts, right? And it reverts because we're going to attempt to decode a Boolean because we are expecting back, based upon this interface, some Boolean return data, but there is no return data. And so when we try to decode this and then ultimately try to return something from this function, we can't. We don't have any return data to decode a Boolean with, right? So we end up just reverting. And we can see if I were to basically modify this and make this actually return a bool, and so I can say return false here, we can go ahead and deploy this new version. So I got my new token here, we put this in, we call the test call function, and it passes, right? Because we were actually able to get some return data for this Boolean, and then that was able to get decoded and then ultimately returned from the test call function. And then we can see the decoded output here was we received false. So this could be a potentially pretty big issue if a system has an interface like this that they're using to interact with tokens, and they're expecting this return value that we can see here in the interface, but the token is maybe something like USDT, which doesn't actually have a return value for the transfer, transfer from, and approve functions. So that is number 5 here. Boom, checked off. And now we can get on to a personal favorite of mine, which I actually discovered while I was auditing the GMX V2 system. I was originally thinking about a really overly complex attack, and I needed something to get this attack to work. And I just so happened to think about, I got lucky and this idea popped in my head. I needed the token transfer to revert. I was thinking extremely hard about how I could get the token transfer to revert, and this idea of blacklisted tokens or blacklisted addresses popped into my head, right? So there are plenty of tokens that have a blacklist feature. So first of all, what is a blacklist feature? Well, USDT is, odd in numerous ways. It also has a blacklisted feature. So let's go ahead and find the transfer function. We can see that we require that the message.sender is not blacklisted. And then similarly, we can see in the transfer from method that the from is required to be not blacklisted. And then let's go ahead and let's have a look at USDC, which is another token that has blacklist. So we'll go ahead and read as proxy. We'll find the implementation, and then we'll go here, and then we'll find, we can go ahead and open it in the BlockScan IDE. And then what we'll do is we'll search for blacklist, and we will just, actually, what we'll do is we'll look for function transfer from. So we can see that we have some modifiers here, not blacklisted, which you can imagine what that does. Requires that the message.sender is not blacklisted, the from is not blacklisted, and the to is not blacklisted. So anybody involved in this transfer from, or anybody involved in any transfer or approval even, cannot be blacklisted, right? And if we look for the first instance of this modifier, we can see it just reverts if this blacklisted mapping is true for the address, right? So that's what a blacklist is. It's saying the transaction will revert if it interacts with an address. So in some cases, this can be used to exploit a protocol, right? If a protocol really needs a transaction to go through, but you can cause it to fail by having, maybe forcing them to .transfer to, where the to address is something that is blacklisted. That's going to be an issue, right? Let's think about what happens in a liquidation, right? In a liquidation, we need to close a position. Otherwise, the protocol might take on bad debt, right? Or the position can go insolvent. And then, that insolvency causes the protocol to take on bad debt, right? So liquidations have to happen. They have to happen fast. But if we can cause them to have to transfer to a to address or something like this, if you had remaining collateral and it got sent to your receiver address or something like this, if that happened to be an address that was blacklisted for the collateral token, the transaction will revert, and that will be a huge, huge issue. So blacklisted addresses, huge issue that really not a lot of people know about. So boom, check off number 6 here. All right, let's talk about subsequent non-zero approvals, and specifically not allowed, when they are not allowed. And so we're going to be going back to USDT, which is an odd, weird token for sure, but there's a reason that they have this. So let's go ahead and let's find the approve function. All right, fantastic. So they've got a comment here explaining why they have this require statement. Essentially what we're requiring here is that if the allowance is non-zero, you have to approve a zero amount and set the allowance back to zero before you can go ahead and change the allowance from zero to a non-zero amount, right? So if you want to change the allowance from an already non-zero allowance, say if my allowance is 5 and I want to go to 9, I have to change it to 0 and then change it to 9. And so why does USDT do this? Why do we want to do this? Well, this is because of the approval front running attack, right? So let's look at this, right? Let's look at this situation. Let's say I approve Bob for, let's say, 5 USDC, or yeah, let's just use USDC as a, an arbitrary token implementation here. I approve Bob to spend 5 of my USDC, right? Now, Bob doesn't spend any. Then I owe Bob $5 more. So I want to increase this approval to $10, right? So that Bob can get his extra $5, right? So what am I going to do? I'm going to send a transaction for approve $10. Let's just, not worry about decimals. Approve 10 for Bob, right? Or I think it would be Bob approve 10, right? If we look at the signatures, it's the spender and the value. So I send a transaction to approve Bob for 10 tokens here. Now, originally, Bob's approval here, so let's say here at this point, Bob was approved for 5. And now at this point, if all goes as planned, Bob will be approved for 10. And that's the end of the story, right? Now, and then what Bob would be able to do is, okay, he can transfer from, and he gets 10 tokens. And that's net aggregate what Bob gets. Let's consider a alternative situation. So go ahead and copy this. We'll bring this over. Now, what happens if right before this transaction goes through to send him to 10, Bob front runs it? He front runs that transaction and he transfers 5 USDC to himself, right? So what does he get? He gets 5, right? And then the approval is of course set back to 0. So he's approved for 0. He can't transfer anymore. But remember, my transaction is still sitting in the mempool. It's about to get recorded in a block, or maybe it's even just later on in the same exact block. And basically the approval goes back up to 10, right? And then Bob can transfer 10 because I hard coded the approval of 10. I said, no matter what, I want to set it to 10, right? So what happens is my original transaction goes through, approval gets set to 10. Now Bob can transfer those 10 tokens. And so net aggregate, Bob gets 15 tokens, but I only wanted to give him 10 tokens. So we have an issue here. And so this is why USDT requires that you're not allowed to do this. If you already had approved Bob for 5, then you can't set the approval to 10. You've got to set it to 0 first. And so then Bob can't do this front running where he transfers 5 and then he, is able to get the full amount later because I set it to 0 and then I set it to the full amount that I want after that. So now what I would do is I would send a transaction to approve for 10, right? And then of course, if I were to see that Bob had front ran this and actually gotten those 5, well then I would have time to, before sending the second transaction, be like, oh, I see that Bob just got these 5 tokens, so I only need to set him to 5, right? And now he can only take 5 here, and so this is 5, and so Bob only ends up with 10 tokens, which is what I wanted him to end up with. And so this is, now I'm protected. As long as I'm sending the right approvals, then I can completely avoid this and we don't have to worry about this exploit. So that is why USDT has these checks and this require statement right here. But it's still something that, as somebody using USDT, you need to be aware of this because this can cause a denial of service in the application, right? It causes the transaction to revert, which can potentially be a knob for a much, much worse exploit in the system that is using USDT. So number 7, boom, checked off. Okay, now let's talk about a really interesting one that will only apply to a narrow subset of systems, but one where we talk about multiple addresses for a token, right? So often or always, systems should not worry about what the exact implementation is of a token, or be worried about what the exact address of a token is. Specifically, if you wanted to implement some sort of blacklist of like, okay, you're not allowed to call this token after a transfer for this token has already happened into the system, or something like this. It's a little bit convoluted and perhaps even a sign of bad design overall, but you should never make an assumption that the balances mapping of a token can only be changed by calling one address. What do I mean by this? Well, there are tokens such as, I think TrueUSD is one such token that actually has multiple addresses which can control the same balances mapping, right? So if I call this address over here, this contract, then calling the transfer function here will change the same TrueUSD balance that is reflected as this address over here. And if you call transfer on this address over here, it will change the same balance. And really, if you think about it, this can apply to any token, right? Because I can just write up a smart contract that's just a wrapper, basically, around the token contract, right? So if I just wrote up a contract, let's say we had the DAI token here, so we had DAI, and then I just wrote a contract that was basically a wrapper around DAI, and I called, if I wanted to call transfer on my contract, it could just basically come back and say, okay, well, I'm going to call transfer on DAI. This token, for all intents and purposes, is DAI when you're interacting with it. If I had all the same functions as DAI and it just delegated the implementation of each of those functions, it didn't delegate call, but the actual implementation of those functions just made another external call directly to DAI. Well, it's essentially just another way to interact with the DAI contract. So you should never assume in a system that the only way to change the balance of a token is by calling the address of that token, or the only way to change approvals or do anything that interacts with the token, right? Because there are some really weird tokens like TrueUSD, and then if you think about it at a fundamental level, anybody can go and create wrappers around tokens. Okay, so number 8, boom, checked off. All right, then number 9 here is somewhat simple, but it's always something that needs to be considered is upgradable tokens, right? So you should never assume that if there's an upgradable token, that implementation will remain exactly how it is forever, right? So for example, USDC is upgradable, right? They can implement technically they can implement any new feature that they want. They could add callbacks to USDC if they really wanted to. They also have features that aren't currently in use that could be put into use, right? So USDC is actually technically a fee on transfer token. It has that capability, it's just not turned on right now. So upgradable tokens and tokens that, have features that are latent, like fee on transfer for USDC, this is something that, should always be kept in mind, right? The behavior today might not be the behavior tomorrow, right? So that's a short and sweet one, but number 9, checked off. Boom. All right, now number 10 here is flash mintable tokens, right? So one such example of this is DAI. So DAI, you can actually borrow a ton of DAI. I can't remember exactly how much. I think up to 300 million or something like this, a significant amount of DAI. You can just flash mint it, borrow it in a single transaction, and then repay it at the end of the transaction plus a little bit of interest, right? So this is a very interesting knob that you have at your disposal to manipulate any system potentially. It's pretty much very similar to a flash loan from a swap, but now there's no swap actually being used. It's just straight up, we'll mint you these tokens for a short period of time for one single transaction, and then you just pay them back. Right, so some tokens might be able to cause some sort of manipulations for a system that's using those tokens because of this. So that is always something to think about. All right, so number 10 here, boom, checked off. Let's go on to number 11. All right, and number 11 here is transfer less than amount. So how do I do a transfer and actually receive less than amount when it's not a fee on transfer, it's not a rebase or anything like this? Well, some tokens, for example, if you specify an amount of let's say type uint 256.max, the transfer will actually go through, and what it will do is it will translate that and say, okay, so we'll just transfer the user's balance, right? So this is an extremely interesting edge case that some tokens could implement, and especially if you're dealing with an arbitrary token, then this is something that you will want to look out for. And in a similar vein to number 1 here, fee on transfer and rebase, this could just confuse the protocol in that the amount that was actually received is not actually the amount that was transferred, right? And that could pretty easily cause a critical vulnerability if these types of tokens are in scope for the protocol. So number 11, boom, checked off. Okay, and finally for number 12, let's talk about tokens with lots of decimals, right? So more than 18, more than expected. Of course, we know that USDC has 6 decimals. Some tokens have, as little as 6 decimals. But what about some tokens that have a lot of decimals? And so here I've actually got pulled up the YAM V2 token, which if we go ahead and we read the decimals of, it actually has 24 decimals. Don't ask me why they need all this precision, all these 6 extra decimals of precision, but they have 24 decimals of precision. And of course, that could confuse some systems, or some decimal accounting only handles tokens up to 18 decimals, or maybe 22 decimals or something like this. They might not support 24 decimals of precision. So that is number 12 here, checked off. Boom, that is all 12 of these things here. And I've even got 2 bonus ones for you, which we'll just write out here. Is we've got bonus, we've got 2 bonus, the first of which is pausable. So pausable tokens, tokens that could be, maybe transferring can be disabled for a period of time. This is similar to maybe something like the same behavior as a blacklist, where stuff just starts to revert, but it could actually be triggered by a centralized trusted address that all transactions would revert. So this is something to definitely consider as a counterparty risk that you're taking on when you're working with a particular token. And also, some tokens will revert on large approvals or transfers specifically. If the approval amount or transfer amount is greater than the UINT 96 for uni or comp, then that's going to be an issue on their side, and they're going to revert because of it. Well, of course, certainly if you're going to be trying to transfer that amount, that would fail, but it might be interesting to see approvals fail when you're trying to just approve a really large amount. If it's bigger than UINT 96 for some of these tokens, that will be a problem. So that concludes every weird edge case, anything you need to think about when it comes to ERC20 tokens and just token integrations in general. Like I said at the beginning of this, go ahead, go through these 12, go through these bonuses, tally up all the ones that maybe you didn't know or maybe you weren't as familiar with. Go ahead and put them in a tweet, tag me in the tweet, and tweet it out there so that, first of all, you remember these edge cases, and we can share these edge cases with everybody else so that everybody finally starts accounting for all of these different edge cases, and hopefully we can get less vulnerabilities and bugs in production. All right, that is all that I have for this video. I can't wait to see you in the next one.